Lesson 54 completed the probability space, omega, f, p. With it in hand, we can finally say what expectation actually is. Until now, E of x came in two flavors: a sum, sigma x times p of x for discrete variables, and an integral, integral x times f of x dx for continuous ones. Two definitions for one idea. Lebesgue integration replaces both with a single one. Here is the key move. Riemann integration slices the domain. Chop the x-axis into thin vertical strips and add up the area of each strip. But on an abstract sample space omega, there is no x-axis to chop. The outcomes might be coin flips or entire Brownian paths. There is nothing to slice. Lebesgue slices the range instead. Fix a value y and ask which outcomes send x above y. That collection is a set in F, and P already knows how to measure it. Now the domain can be anything at all. The construction comes in three stages. Stage 1. Indicators. For an event A, the indicator 1 sub A is 1 on A and 0 elsewhere, and we define its integral to be exactly P of A. A finite combination of indicators is a simple function, and its integral is just that weighted sum. Stage 2. Any non-negative x. Take every simple function sitting below x and define the integral of x as the supremum of their integrals. Simple functions climb up toward x from underneath, and their integrals climb with them. Stage 3. A general x. Split it into a positive part and a negative part, x plus and x minus, both non-negative. The integral of x is the integral of x plus minus the integral of x minus. X is called integrable when e of the absolute value of x is finite. That is precisely the condition that stops stage 3 from handing you infinity minus infinity. The result is one object. E of x equals the integral over omega of x dp. Expectation is the Lebesgue integral of the random variable against the probability measure itself. For a discrete x, this collapses straight back to sigma x times p of x. For a continuous x with density f, it becomes the integral of x times f of x dx. One definition, two familiar faces. And it covers cases neither old formula could: a mixed variable that is part atom and part density, or a variable living on a space with no density at all, like a function of a Brownian path. No special cases required. Lebesgue integration builds expectation in three stages. Indicators give integrals to simple functions. Simple functions climb up to non-negative x, and positive minus negative parts finish the general case. The payoff is a single definition. E of x equals the integral of x dp that works on any probability space and swallows the discrete sum and the continuous integral as special cases. Next, the convergence theorems. Monotone convergence and dominated convergence tell you exactly when you are allowed to swap a limit with an expectation.